speaker of this morning session is Abhishek Dahr from ICTS Bangalore in India. He's going to tell us about page curve entanglement dynamics of a gas of freely expanding non-interactive fermions. Please start.
First, I would like to thank the organizers for this invitation to this great meeting and this beautiful place. So this I'll talk about work which is done with Salah, who is a postdoc at ICTS, and Manas, who is here. And it's a very simple model of trying to understand the so-called page curve entanglement dynamics. So I'll start by giving some motivation of I mean, it's a very simple model, but the motivation is kind of important. Okay, so the motivation is basically it's related to the black hole information loss paradox. So let me just give a very brief introduction to the basic statement of the problem. So this is, I mean, I'm in a place which is full of string theories, so this is what I learned, I mean, from talking to them. And I don't know too much about quantum gravity, but I think it's sort of an accurate statement. Okay, so a black hole, I mean, is basically, if you have, let's say, sort of distribution of gas which are interacting by gravity, then eventually, if the mass is big, then they attract and they collapse and form a black hole. And classically, black hole is something from which nothing can escape. This is image of a real black hole seen recently. Then, if you look at quantum physics, a quantum description of a black hole, this is what Hawking described in 1975. Then, according to in the quantum description, a black hole can radiate. And then the idea is that it can keep radiating and eventually vanish, turn completely into radiation. Okay, so now what's the information loss paradox? So the initial, before the black hole is formed, you have a gas which can be described by a pure state, let's say. It has a wave function which has detailed information of what the star is made of and where the atoms are located and so on. And then eventually it forms the black hole, and then you have thermal the final state is just radiation, and the radiation, radiation depends on very few parameters like the total mass, charge, and angular momentum of the black hole. Okay, so it looks like all the information about the initial state is lost, and so in some sense this is the paradox. Okay, one way to sort of quantify this paradox is by defining this idea of entropy. And what Hawking did in 1975 is sort of semi-classical calculation of the entropy of the radiation field. And what he found is that the radiation entropy keeps increasing up till the time the black hole evaporates completely. Okay, so now this is slightly problematic because, and this was kind of pointed out nicely by Page in '93. And so the idea is like, let's say you have a black hole and then there's radiation. So this is like a system. The black hole and the radiation should be part of like two subsystems. The entire universe is divided into black hole, which is one subsystem, and the radiation. So initially, let's say you don't have any radiation; it's just the black hole, and it's unentangled with the radiation. And then it starts it starts radiating. So in some sense, you can think of like there's a Hilbert space where which is divided into the system, the black hole and the radiation. And as it radiates, the Hilbert space of the black hole is decreasing, and the Hilbert space dimension of the radiation is increasing, right? So if you assume that they are kind of the black hole and the radiation are maximally entangled, then what you expect is that, so initially of course the entanglement is zero, and then at any time the entanglement will be given by the system whose Hilbert space dimension is smaller. Right? Okay, so at around the time when, let's say, half of the black hole is evaporated, then you expect the entanglement should be maximum, and then the entanglement should go down. Okay. So So this, I mean, page, calculation was purely a sort of static calculation. There's no dynamics in it, but that's the basic idea that eventually you expect that entanglement between the black hole and the radiation should increase, and then after some time, which is now called page time, it should start decreasing. And this, and the time at which it starts decreasing, it should be roughly like when half of the black hole has evaporated. So now, this calculation was of course classical, semi-classical, but it's expected that the calculation should be good as long as the black hole is quite, is kind of large. So it should be valid at least till, the black hole is like almost evaporated. So then there's a sort of, so this is one way of stating the paradox. Like this calculation seems to say that the entropy keeps increasing, but entanglement entropy should really decrease. Right? Okay, so demonstrating this kind of the page curve in a quantum gravity calculation would of course resolve the paradox, and I think recently this has been achieved. And at least, a lot of people think now there's no more no paradox. Okay, I just want to point out, a sort of a nice article by Christian Mays, who says actually, if you really think about it, maybe there's no real paradox. So it's written no information or horizon paradoxes for the statistical mechanician in the street. Okay, so this is a nice article which kind of presents a different viewpoint. Okay, so now what we want to do is basically, okay, so again, this is in a nutshell, this is the statement of the problem. So this is entanglement entropy versus time of entanglement between a black hole and the radiation. From Page's ideas, you expect something like this. So there's some time, characteristic time at which the entanglement is maximum and then it should decay. And Hawking's calculation gives something which keeps increasing. Okay, so now what we wanted to do is basically look at a simple model which reproduces these basic features of the page curve, and it's a kind of you have dynamics of and the model that we look at is kind of has been studied extensively earlier, starting with this seminal work of Calabresi and Cardi, where you just look at, okay, so the main difference that from our work is like this typically look at infinite systems and you look at entanglement, how it evolves with some like initial condition. Okay, so so there's been a lot of earlier work in the which is very similar to the model that we studied, and so this I'll once I describe the model, become clear what's the difference with this earlier study. So around the time when we started doing this work, there's actually two other papers appeared on exactly the same question, like trying to reproduce the page curve in a very simple model in just a non-interacting gas. And then there's more recent work on interacting systems. This is something which Manas will talk about, interacting spin chains and some other models with effective interactions. And then there's also some other recent papers looking at interacting systems. Okay, so the work that I will talk about is completely non-interacting fermions, and what I will do results from exact microscopic numerical calculations of this entanglement, and trying to understand it using sort of semi-classical hydrodynamics. And what we find is there's a very nice agreement between the two. Okay. So of course there's no gravity, no interactions. So, but I think the model sort of captures at least some features, and it shows that like while the entropy of radiation can keep increasing, but you can still get a page curve. So I think it does explain some aspects of the information paradox. Okay, so second motivation is of course like entanglement is one of the important measures of quantumness, and understanding it even in very simple models is kind of okay. So this is the model. We have a lattice system which is in principle like semi-infinite. And so this is what I'll call the system, and this is like a path or the environment. And so initially we have like fermions like filling this box, and this is completely empty. Okay. And then things start escaping, and so this is like roughly, this is like a black hole which is radiating. Okay. Now, if you look at this model, it's clear that you will get something like a page curve, because initially we start with a pure state, which is completely placed here, and there's zero entanglement between these two. And then this gas starts escaping, so eventually all the gas will escape into the environment. Right? This is infinite, so everything will escape. And then we expect the entanglement to go to zero. Okay, so it has to follow roughly some features of the page curve. But we want to understand like precisely how does this happen, like what is the behavior of the entanglement. Okay, so now, we always prepare, look at initial states which are kind of Gaussian. So any Slater determinant is Gaussian, and in the sense that any higher order correlation can be expressed as single particle correlations. So this makes calculations very simple. Okay, so this is the model, and so it's just a tight binding hopping Hamiltonian. So it's homogeneous everywhere except we introduce a defect at the junction between the system and the bath, and this is kind of important to have this defect. This defect kind of helps in generating entanglement in the system. So the kind of defect we look at is, so everywhere there's a hopping G, which we take one everywhere. And this can be different, and we can also have some on-site potentials at these two sites. Okay, so so I hope this is clear. This is the kind of defect we look at. Okay, so I mean the reason we put a defect is if you didn't have a defect, then the entanglement growth would be very slow. In fact, in this case, you can show it's a logarithmic growth. Okay, and in fact, you can't understand it using just Euler hydrodynamics. You need fluctuations, so it's a slightly more complicated problem. So that's why we put the defect, and in that case, the growth of entanglement is linear in time. Okay, so let me now talk a little bit about the kind of defect that we look at. Okay, so there are three kinds of defect that we study. So the first defect is, let's say, what I call a density defect. You could just put some on-site potentials at these two sites.
Sorry, can you say again? Yeah. What was the comment about logarithmic growth?
If you don't have any defect, supposing it's a completely homogeneous system,
yeah, and
you start with a field like initial condition, like a field box here, then the growth in entanglement would be logarithmic in time.
Okay.
And once you put a defect, then it's a linear growth.
So defect means the hopping is very small.
Just at this site, if you either you could put some potential on-site potentials here, or you could make that like the hopping different.
Yeah. Any different hopping would.
Any different hopping would. So these are the three kinds of defects we study. Hopping defect is just you put some different G. The density defect is you put some on-site potentials. And the conformal defect is kind of interesting because you can put some on-site potentials and G in such a way that if you look at the transmission of like particles across this defect, it's independent of wave vector. Okay, so you can arrange things in such a way. And there's just one parameter, lambda, which is the transmission coefficient. Okay, so this I just show the transmission coefficient as a function of wave vector for different kind of defects. So this is the conformal defect where it's completely independent of K. Okay, so so I hope this model is clear. I mean, so we have a tight binding model with initially it's all field, and then we let it evolve. Okay, so the spectrum of the single particle energy levels is just this. And okay, so initial state is a pure state and it's a zero entropy state. Okay, so now, like I said, for Gaussian, this kind of Gaussian initial states, the 2-point correlation matrix contains complete information about the state. Its evolution is very simple. And once we know this, we can compute things like various physical observables, like the density profile. We can ask how many particles are there after time t, what is the fluctuation in the number of particles, and so on. So all this can be computed. And then the entanglement entropy is also can be actually completely obtained from this correlation matrix. So the reduced density matrix is, because it's a Gaussian state, can be written in this form, where this matrix D out here can be obtained from the correlation matrix by just looking at the correlation matrix in this in just the subsystem. Okay, so if I look at the correlation matrix in the subsystem, so there are n sites, so it's an n cross n matrix and n eigenvalues, then the entanglement entropy is just given by this formula. Okay, so from the microscopic points, one can just numerically compute all these objects. So that's straightforward. And then I'll talk about how one would use hydrodynamics. Okay, so
Sorry, could you just point out on the previous slide where the time dependence is?
So the correlation matrix it will evolve, like initially it starts with something and then it evolves under. Okay, so now the hydrodynamic description, it's like exactly what one does in GHD, except it's a very simple, much simpler generalized hydrodynamics. There's no phase shifts. So let's say at the hydrodynamic level, we think of it as a gas of quasi-particles which are localized in position and momentum at this point xk, with some spread of order h bar. And let's denote this phase space density by ntxk. The quasi-particles have velocities vk, and these are completely non-interacting quasi-particles, so there's no phase shift and so on. And so this is basically the Euler equation. Okay, so this again is basically like a kinetic equation with no partition terms. And one other way, which is kind of interesting, is that this one can think of as a coarse-grained Wigner function. Okay, so let me just talk about how it's connected to the Wigner function. So, I mean, given a many-body pure state, so in this case, I can just construct a single particle density matrix which has the same information about, which has complete information about the state. Okay, then one can, there's a prescription for constructing a Wigner function starting from this single particle density matrix. And then if I constrain this Wigner function over some scale h bar, then one obtains the phase space density. And for the Wigner function, one can write an exact evolution equation. And then to leading order in h bar, one can show that it satisfies this simple Euler equation. Okay, so now how does one compute entropy from this entanglement entropy from this from the single particle density? Okay, so this is kind of bit. Okay, so let me try to explain this. Okay, so things like density profile and so on are easy to compute from the phase space density. I just integrate out momentum to get position density. Okay, and then one can compute something which I'll call a hydrodynamic entropy. Okay, so what is this object? So if I look at locally, there's a phase space density is just like a Fermi distribution, a local Fermi distribution. And if I integrate over k, then this is the formula for thermodynamic entropy of a Fermi gas, right? F log f plus 1 minus f log 1 minus f. That's just the hydrodynamic entropy of a Fermi gas. Okay, so this is like locally I have hydrodynamic entropy. And afterwards I'll try to explain that this is actually like a Boltzmann entropy. Okay, so this has again, this object has been earlier used in various studies to also compare entanglement entropy using hydrodynamics. Okay, so now, so once we know this locally, we can compute the hydrodynamic entropy of the system and independently of the reservoir. Right? So by integrating this local entropy over just the system part, we get the hydrodynamic entropy of the system. And we can get it for the reservoir. Right? Okay, so this is how we use hydrodynamics to compute entropy. Right now, it's not clear why this should be the entanglement entropy. It's just some entropy. Okay, so now the other question is like, how do you solve this equation for this particular setup? Okay, so I mean, if it was on the infinite line with no then it's very easy to solve this equation. But here one has to remember that there are this defect which scatters the particles. So there's some transmission and reflection of particles, and then there's a finite. There's a wall here. So one has to solve this equation with taking into account these boundary conditions, that there's scattering here and there's a wall here. Right. Okay. So these are the boundary conditions. We have to solve this equation with this kind of boundary conditions. So I mean, numerically, if you see how the phase space evolves, so initially it's like this is space and this is momentum. So everything is confined on this half. So this is and this is the density is 1 everywhere and 0 outside this. And then so the left movers go this way and the right movers go this way. But what's important is that because of the defect out here, the density now is less than 1 here, and it's also less than 1 here. Okay. So if you didn't have the defect, the density would always remain 1, and so there would be no entropy production. But because of the defect, I mean, as the phase space density evolves, you also generate entropy. Okay, so this is how the phase space density evolves, okay, so then we can actually write an exact solution for this evolution. So the basic idea is that on the infinite line, if there were no defects, then you just have this, you just boost the initial density and you can write the solution at any time. But now with the boundary conditions, one just has to take into account that there are these multiple reflections at the defect and at the wall. And so you can write a series series solution. This is what one would write, for example, for diffusion with absorbing boundaries or so on. Okay, so here one just has to take into account that there are some number of reflections, and then you just boost it accordingly, like how, where does the density come from. Okay, so we have an exact solution for the phase space density, and now let's see how it compares with the microscopics and the hydrodynamics. So this one we just look at the simplest observable, which is the density profile. So initially it's a domain wall, so it's 1 and 0 everywhere. And then slowly things escape, and this is how the density profile evolves with time. And so here the points are from the microscopic simulation, and the solid lines are from the hydrodynamics, and you can see they agree perfectly, except it doesn't reproduce this kind of oscillations and so on. Okay, so these are, because it's non-interacting, you can do simulations for, so the path is like maybe it has a few thousand sites, and the system has maybe 100 sites. Okay, so we want to look at time scales till the sort of the particles reach the end of the hit the other wall. Right? Okay, so this is how the density evolves. This is how the current evolves. So the current is kind of constant till some time. So this time is what we will eventually call the page time. So this is the time at which the fastest particle kind of goes to the boundary and then comes back. Right. So that will be twice the length of the box, which is n. Divided by some Fermi velocity. So at this time scale, then it realizes that it's a finite system, so that then the current starts decreasing. Okay, so so the main observations are that the current, if you look at it, it's constant, and there's some power law decay, and we can understand this decays completely from the hydrodynamic theory, and it depends on the kind of defect and so on. Okay, so next I'll discuss the entanglement comparison between the exact numerics and the hydrodynamic theory. Okay, so let me just remind you that there are two different computations. One is the microscopic entanglement entropy, which we expect, of course, that the system entanglement and the path, they should be identical. So this is one thing, one object we compute, and then the hydrodynamic entropy you can compute it for the system and for the bath. Okay, and this of course need not be equal. So we compute all these three quantities and compare them. Okay, any questions? I hope this is clear. Okay, so now let's look at the numerics. So there are these three quantities: the exact entanglement entropy, and the system entropy, and this is the reservoir entropy. Okay, so the circles here are the entanglement, and so it has the page kind of form. It grows linearly, and then right up to this time, which is the page time, and then there's some power law decay. And then if you look at the reservoir entropy, so initially it also increases linearly with time, and then it keeps increasing. Okay, so this the reservoir entropy just keeps increasing with forever. Well, the system entropy, it increases and then it starts decreasing. Okay. So now what's most interesting is that the system hydrodynamic entropy and the exact entanglement entropy, they kind of agree almost very closely. Okay, so there's a remarkable agreement between the microscopic entanglement entropy and hydrodynamic system entropy at almost all times. While the bath entropy, it just keeps increasing with time.
So can I ask about this?
Yeah.
So if you didn't have your defect, so that there was log t growth of entanglement entropy, hydrodynamic entropy would still increase linearly?
The hydrodynamic entropy, if you just do the semi-classical, it would actually it will be completely zero. It doesn't increase at all.
If there's no defect.
If there's no defect, right? Yeah. So in some sense, the semi-classical calculation fails completely. In that case, there's recent work where if you include fluctuations, like hydrodynamics with quantum fluctuations, then you can get the log t growth. So the log t really is in some sense more quantum. Right? Yeah. Okay. So this is looking at it like finite size effects. If we keep increasing the system size, so the scaling is kind of quite simple. If you scale time by n and entropy by n, then they all collapse. And what you also see that as you go to larger system size, actually the agreement with the hydrodynamic theory gets even better. Okay, so from the hydrodynamics, one can do a lot of computations. So this is the series which has converges fast at early times, and so one can get this early growth in entropy, which is linear in time. And then if you do a Poisson resummation, you can get the behavior at large times and so on. And what we find is basically, so these are the main interesting results. So at short times, entanglement grows linearly with time for all kinds of defect, where the prefactor depends on the kind of defect. The current is constant till the page time. So this is up to the page time. This is what you find for the growth of entanglement. And after that, there's a power law decay. And this power depends on the kind, the precise choice of defect. Okay. Okay. So one question is like, how much entanglement do we get in this kind of completely free system? So if you look at till time t, so this supposing we just look at the conformal defect, which is characterized by a single parameter lambda, which is probability of transmission. So lambda square is actually just the probability of transmission. So the number of particles which escape after time t is grows linearly with time, and the total entanglement entropy from the hydrodynamic formula at short times is given by this formula. And so if you ask if you choose lambda square is half, then this is maximum. And then if you ask what is the entropy per particle, then it's actually log 2. And the peak entanglement value is, so this is per particle, and at the age time, this is what you get. And so, I mean, this is kind of course, small compared to the maximum entanglement you can get from in this system. Okay, so the other thing that we looked at is the number fluctuation. So for this non-interacting systems, which are prepared in Gaussian states, there's an exact relation between entanglement entropy and the full counting statistics. So basically, you can the entanglement can be written as a series in the current cumulants, where these ANs are exactly known constants. Okay, and quite often it has been seen that actually just the second cumulant is already quite close to the entanglement. So you don't really need all the terms in the series. This is something we checked in our computations, and so in our case, of course, we can compute the number fluctuations also from hydrodynamics. So what we found is that the entanglement let's say for some system size, the entanglement is given by this curve, while the number fluctuations is given. So except near the page time, there is pretty good agreement between these two objects. So the second cumulant basically follows the entanglement entropy, and there are some clear deviations near the page time. Okay, so now, okay, so let me talk a little bit about, okay, so one question is, of course, why is there such a good agreement between this, the hydrodynamic entropy and the entanglement entropy? So one is what is known as a fine-grained entropy, the entanglement entropy. And the other entropy that we consider hydrodynamic entropy is really a Boltzmann entropy. So let me try to explain this a bit. So the entanglement entropy, of course, is like if I have a pure state, I divide it in two parts, and this is the usual definition. The Boltzmann entropy, sort of the general definition of Boltzmann entropy is like if I have knowledge of some set of coarse-grained variables, let's say, for example, the density profile, then I can ask, like, given a density profile, how many microstates are there which produce this density profile? So if that is gamma, then the Boltzmann entropy is just a log of gamma. So this is defined even in a non-equilibrium state, and in equilibrium, of course, it's the usual entropy, usual thermodynamic entropy. But I mean, so this is a very nice concept which can be used to describe irreversibility and so on in completely unitary dynamics. Okay, so actually there's a recent paper by us with several people where we studied just evolution of this Boltzmann entropy again in free fermions during free expansion. Okay. And there the entropy that we used, so this I'll try to explain, is actually identical to the hydrodynamic entropy that I just so let me try to explain this a bit more. Okay, so now this yang-yang entropy, so the way I present it is it looked like basically a local Gibbs equilibrium entropy. So in space, if I just look at locally, then I have a Fermi distribution, and for that I can construct a thermodynamic entropy, and then the total entropy is just the integrated entropy, right? Then there's another way to interpret this entropy, which is like as a von Neumann-Jaynes entropy, and this is basically based on the idea of the Boltzmann entropy. Okay, so here the idea is that supposing that we do not have the precise density matrix, but we have information on the expectation value of some observable in that state. Okay. So then according to Jaynes, the best case for the density matrix is one which maximizes this object trace minus trace rho log rho subject to this constraint. Okay. So now in our case, supposing we do not know the correlation matrix exactly, but what we know is the phase space density, which is some constraint, which is actually a constraint description of the correlation matrix. Okay, so then if we follow this Jaynes prescription and maximize S over all density matrices which satisfy this constraint, then it can be shown that you get exactly this yang-yang entropy. Okay, so in that sense, one might expect that in some situations, these two, then it should be close to the entanglement entropy. Okay, I have some time.
Yes. Like 20 minutes.
Okay. So anyway, so let me talk a little bit about this earlier work with all these people, where we looked at again evolution of Boltzmann entropy during thermalization of a freely expanding gas in a finite box. Okay, so this earlier study was different because it was a finite box, where of course you don't expect to see a page curve, right? Because it should saturate to some value. Okay, so in this case, what we could show is that so if you have particles in a box, then of course there are you can form plane wave states which are delocalized, but it's also possible to construct sort of a single particle basis of states which are localized both in position and also in momentum. Okay, and this they are localized with satisfying this constraint. Okay, so let's denote this single particle basis states by psi alpha, where alpha is the is where the states are localized. Okay, so now let's say this is the number operator which corresponding to the occupation of this states n alpha. So then, of course, I can write the density matrix in this basis, right? I could write this the density matrix in this, and I would get rho alpha beta, and that would have complete information about the state. Okay. But now, let's say we define a we have a coarse-grained description where we define macro variables, where we only look at the diagonal expectation value of this number operators. In some microstate phi, okay, and so let's call this d alpha, and so this is a coarse graining of the full information, right? So the full information is there in the density matrix rho alpha beta, but supposing we just look at d alpha. Okay, so what we could also show is that this d alpha is actually can be directly related to the Wigner function. By just coarse graining in both space and momentum, and this d alpha is positive definite, so it's actually like a phase space density, then if we follow Jaynes' prescription, then one can show that the corresponding Boltzmann entropy is exactly given by this definition, which looks, which you can see is again is basically the yang-yang entropy. Okay, so in this work we again looked at the evolution of this entropy. So the phase-space distribution evolves in this phase. So again you start with half field case, and then you can see structures developing in the phase-space distribution, and eventually it thermalizes. So even though it's a non-interacting system, it thermalizes to some GG, and then what's interesting is that you can compute Boltzmann entropy, which actually increases. I mean, it's not completely monotonic, but it increases, and this change is exactly log 2, and it shows in some sense thermalization. Okay, so maybe one natural question is like whatever how generic is this, like this in particular the agreement between the hydrodynamic and the microscopic entanglement entropy. So in particular, the kind of initial condition we looked at is zero entropy initial condition. And then one thing that we have been investigating recently is like finite entropy initial conditions. And so Manas will present more details for interacting spin chains. And there, one of the things that we find is that if we do the same computation, trying to compare Boltzmann entropy with the entanglement entropy, so the generic thing is kind of a bit different. There, what we find is that before the page time, the Boltzmann entropy of the bath kind of agrees with the entanglement entropy. So the entanglement entropy has this in feature, and the Boltzmann entropy of the bath agrees with the entanglement entropy till the page time. After that, it keeps increasing. On the other hand, the system's Boltzmann entropy. So this is a state which initially has high Boltzmann entropy, so it's completely different from the entanglement entropy. So it starts from high entropy, and then after the page time, it seems to agree with the entanglement entropy. Okay, so this we don't have a full understanding, but this is something you see even in non-interacting systems. Yeah.
That's intuitive, right? Because you basically, if you have a small system and like most of your entropy, it comes from like entanglement with the outside world, whereas if you contain most of the system, then most of your entropy comes from like entanglement with other degrees of freedom inside the subsystem you're in.
Okay, no, but
That
agree so well with the entanglement.
That starts out with almost no degree.
Sorry?
The bath starts out with no entropy of any kind, right? It's just no ground state or something.
Right, yeah.
And so then I guess when things come into it, they're entangled with the system. So it's sort of
Right, yeah, but it's not clear that the Boltzmann entropy should agree with the entanglement entropy, right? Okay. In some sense, okay, yeah, maybe, yeah, okay.
It's not true, but it seems intuitive. That's all I'm saying.
But in fact, if you change the initial condition, then it doesn't really agree that well. So it seems to be.
He's saying that even if the bath starts out at zero entropy, you could change the system's initial condition.
Right. Suppose you start the system with a domain wall and the bath is vacuum.
Yeah.
Then the agreement is not that good. So
I see.
So.
Yeah, but because that's the degrees of freedom are different. Right?
Yeah.
They're not just free fermions.
Yeah, this is for interacting spins, but it's true even for free fermions, like this picture.
Actually, how's the Boltzmann entropy defined for the interacting system? Is it defined the same way with respect to like the distribution function?
The Boltzmann entropy, yeah, it's defined. No, you just like partition it into blocks, and then let's say in each block you measure the magnetization and the so you do some coarse graining, and then you just count number. Okay, so right here. So there's some. Okay, so maybe I'll just conclude. So basically, what the idea is to have a simple model which captures some basic features of the page curve. So this is the page curve in the black hole, and this is what we find. What's really interesting is that semi-classical generalized hydrodynamics allows analytic understanding of this page curve, the short time, long time asymptotics, and so on. And then what's also really interesting is that this entropy agrees and then similar to what is observed in the black hole, you find that the path entropy always keeps increasing forever, right? The system entropy kind of follows the page curve, but the path entropy actually is completely different. So this is, in some sense, it's similar to what is observed in the black hole. Okay, so then these other interesting questions are, this is something we are studying, like finite entropy initial conditions and effect of interactions, and this connection with Boltzmann entropy. So this is, these are the two, so this is the non-interacting gas and the interacting spin chains. And this is the paper which we looked at Boltzmann entropy. So I just want to say that Masaki actually has a nice review in the CONMAT Journal Club on our paper, which explains things in a very nice way. Thanks.
Thank you very much. Are there any questions?
So do I understand this page curve like correctly that so the reason why it goes down is basically because your black hole gets empty.
Yeah.
And then when there's no more black hole, then okay, there.
Yeah. I mean, so it's clear it has to happen, like in this kind of. I mean, that was Page's basic argument, right? Like, as the Hilbert phase dimension of the black hole decreases, it has to.
Is there any reason why you can't do the same thing in higher dimensions?
In higher dimensions?
Like 2 dimensions, like, I don't know.
I mean, of course, you will get the same thing. I mean, the calculations, I don't know how much you can do analytically.
But the hydrodynamics for 2D free fermions.
Right, yeah, should be more or less the same, but still, okay, I don't know. Yeah, like, I don't know how you would put defects and so on. Yeah, maybe it's possible.
So it would be slightly more realistic in the sense that you actually have like some filled black hole. Okay, I don't know.
Any other questions?
The defect you need to put in exactly where you put the boundary, I mean, where you put the domain wall, or you could.
Yeah, exactly at where we put the domain. I mean, you could put it differently, things would change a bit, but not so much.
Where did the defect enter in the hydrodynamic picture, like you had the Wigner distribution? Is it a function that...
In the equation, of course, it just comes as a boundary condition when I solve the hydrodynamic equations.
And then if you don't have it,
Yeah, if I don't have the defect, then the semi-classical hydrodynamics won't work. Okay, so then if we do just the same calculation, because the phase space density just stays 1 and 0 everywhere. Okay, so then the entropy just doesn't grow at all from semi-classical. If you do the microscopic, then like what I said was it has a logarithmic growth, and to understand you don't need to go beyond you need to take into account fluctuations in the hydrodynamics.
Any other questions? If not, let's thank Abhishek again.